Alright, hell yeah. So we have a statics problem, and this was given to me by a college student, so that's pretty sweet. So this is a professor pick, and hell yeah, I don't know if this comes from a book or if, probably somewhere. But anyway, so, and we're going to do this one fairly fast. I did a 3-hour version, that's going to be for tomorrow. So we're going to do 2 free body diagrams. What this problem entails is we have a block with mass. That's it. That's all that's going on. This is a friction problem. We're not interested in the friction right there at all. We're interested in the friction right there along that surface and that surface. And so it's tricky because usually we just have a mass on a surface, and that's going to cause the friction, and we're going to pull on that. But now we have the force of friction. We have a frictional force on top of a mass and below a mass. So this post is our mass, and we have a frictional force top and bottom. Alright, so let's just rally this out. So I'm going to draw a free body diagram of this member. And a couple things to do is just to remove the post, and you stand under here, you know what I mean, and then hold that point up. And what are you gonna be, feeling? And is it gonna be the same if you start to walk and then stand right underneath the weight? And then think about it. Let's say you moved to this location and had to stand under. Let's say you moved really close to there and still had to support this thing. And just kind of think about that and see what the leverage would do. Anyway, it's going to be half here. It would be a full weight there. Here it would be twice the weight. All right, so let's move on. This is a pin connection, so we have an AY, a force in the vertical direction, and an AX, a horizontal force. I'm just going to show them as positive. Cool. Over here, we're going to have, I'm just going to show a positive BX, and then we're going to show a positive BY. We're just assuming all the forces are positive. Now this, is going to be right in the center, and so we're going to have a weight. So this weight is due to the mass, and that mass is 200 kilograms, and we're going to be using gravity, so this is just mg of 9.81, and that's meters per second. 1 kilogram times 1 meters per second squared, and sorry for not saying the second squared on that. This is equal to 1 newton, so this weight will be in newtons. 200 times 9.81. Well, keep that in mind just for a sec, because what we're interested in mainly is the load on this post. That's kind of all we're doing with this free body diagram. We're just figuring out what this load BY is, because we know that the free body diagram of the post, we're going to have an equal and opposite reaction. So this is going to be BY on the post. Now the post itself right in the middle has weight itself. That's going to be 20 kilograms times 9.81. Cool. And let's do this one. Let's say it was 10 times 9.81. That would be 98.1. We have double this. So that's going to be 190. What would it? 196.2. Hell yeah. So this is going to be 196.2 newtons. Booyah. And I'm just going to double check. 20 times 9.81. Hell yeah. Alright, so that's going to be the weight down on the post. And then we have some, this is going to be 0.75 meters, and this is going to be 1 meter. We have a component P, and this is going to be 300 newtons. In the long video, I definitely segue into showing how a triangle, these dimensions are the same thing as the representative as the components of a force. So 3/5 is going to be, so 3/5 of P is going to be in that direction, 4/5 of P is going to be in that direction. Booyah. So we're going to have this horizontal component is going to be 4/5 times P. Always get your denominator to be a factor of 10. So this is going to be 8 tenths, and then we have 300 newtons. We're just going to get rid of a 0, and we have 8 times 30. Don't know it, but 8 times 3 is 24. times 10 is 240. So we got 240 newtons there, and that's going to be this horizontal component. So we have 240 newtons. The vertical component of P is going to be 3/5 P. Get this denominator to be a factor of 10. That's going to be 6/10 P. These are the same ratios, and that's going to be 6/10 times 300 newtons. All right, let's get rid of the 0, and we got 6 times 3 is 18, times that extra 0 is 180. So we have 180 newtons right there. So those are the components P, and they're acting right there. Hell yeah. So this is a free body diagram. We can just pretend like this post is floating in outer space. Something is pushing down on it. The weight is pushing down on it. This is pulling up on it. And then we have CY, the ground, is finishing the deal. So we have the sum of the forces in the Y direction right here. Yeah, and we're kind of skipping a step. We didn't figure out what BY was, but let's go for this. Is 0. So we're going to have negative BY minus 196.2 newtons plus 180 newtons. And then, so 1, 2, 3, and then plus CY is equal to 0. Cool. So we have two different things here. We need to come back up to this one. I should have just done this first, getting it out of the way. But what we're going to have is this mass is evenly supported between 2 points. So that should just scream that this is going to be half. But we'll do it correcto. You know, I mean, we're going to sum the moments about A. Is going to be 0. And if we do that, these forces go through A. So they're not part of generating a moment about A. This is the force that generates a moment. It's a distance of 1.5 meters. This force, BY, is twice the distance. So keep that in mind. Twice the distance means it's going to have twice the leverage. So it only needs to be half as potent, you know what I mean? And BX goes through A. That doesn't generate a moment. So hell yeah. So we have a negative, so summing the moments about A, we have negative 1.5 meters times this 200 and then 9.81. That's going to be a force in newtons. That's the units on that. And then the BY is going to be a positive 3 meters times BY. Those are the moments, and they sum to 0. Solving for BY is just getting this to the other side and dividing by 3. We have 1.5 divided by 3. So BY is 1.5 divided by 3. That's just 1/2. And then times 200, 9.81. So this is going to be a 1/2 times 200, 981, which is, you know what I mean, those cancel, so we have 100 times 9.81, and we have 981 newtons. So hell yeah, so there is BY. And I'm going to do that. Alright, booyah. And then we're just going to come up here, and we're going to solve for CY. So CY is getting this stuff to the other side. We're going to have a positive BY, so we're going to have 981 newtons. And then we're going to subtract, and then this is going to be positive on the other side, plus 196.2 newtons, minus 180 newtons, and that's going to be CY. And again, you know what I mean, over here we're going to have plus 981 plus 196.2 minus 180, oh, bummer. Yeah, these are negative. Yeah, so this was right. So it's negative 981 minus 196.2 plus 180 plus CY. But if we want to solve for CY, we got to get all that stuff to the other side. So CY is equal to, you know what I mean, that plus that minus that. And that's what we have. So, booyah. All right, let's just plug and chug. So this comes to 997.2. Hell yeah. Alright, so now that we found our CY and BY, and just keep that in mind because those are the normal forces. at those frictional joints. And so we have a couple more forces here. You know, I should have just thrown them in. But we have this 240 in this direction. They have to be balanced by a CX and a BX. And they should be in this direction. Some of the moments will tell us, but this is you know, the forces in the middle, and then those are the resisting forces on the edges. So hell yeah. So if this is BX, this BX is good to go, and this AX is actually wrong. I'm just going to do that to show, this is my little sign to say, hey, it's opposite. You know what I mean? Because it represents like, hey, it should be a negative, or, you know, it should be a positive. So it's like a sign change convention. That's my convention that I'm going to use. All right, but booyah. So now the sum of the forces in the x direction, I'm going to have two unknowns. You know, both of these have to add up to 240. I want to know what they are. And here's the kicker. This horizontal component is not at the halfway point. So in the longer video, we talk about, you know, like how to do this fast. And the cool thing is you do proportions. So this total length is 1.75. And so this component is going to be 1 divided by 1.75. And this component is going to be 0.75 divided by 1.75. This is the bigger ratio. And so if the force, the horizontal force, is closer to this point, it's the same thing as having a plank. And it can be difficult to see this horizontally. But if I have a plank and I have a force over here, like, hell yeah, this is going to see more of that force as a percentage. This is going to see less of that force as a percentage. Those two percentages are going to equal 1. So that's kind of what's going to happen. If the force is in the middle, both these are half and half. Half plus half is equal to 1. So, booyah. And 1 and 1/7 plus 0.75 and 1/7 is just 1.75 divided by 1.75. So cool, this is the larger ratio. And so we can say that CX is equal to 1 divided by 1.75 times 240. And we can say that and BX is the smaller ratio, 0.75 divided by 1.75 times 240 newtons. Okay. So let's do it kind of the slower way, and we're going to sum the forces. No, we're going to take the sum of the moments about B. That's how you get rid of this component that we don't know. And all the vertical components go through B. And so the only two forces generating a torque are CX and this 240. This 240 from B generates a positive moment. So we're going to say that's going to be 1 meter positive times 240 newtons. CX generates a negative moment minus, it's a distance of 1.75 meters, and then we have CX. Some of the moments have to equal 0. Let's get this to the other side, and then we have CX, and then we're going to divide this by 1.75. And you can just see that CX is 1 divided by 1.75, meters cancel as units, times 240 newtons. And that's what we had right here. And then once we have this, we just sum the forces in the x direction. And it just really spells itself out, because 240 has to equal, well, this plus that. And both of those have to equal 240. So the proportions have to sum up to 1. And so we have 200. So sum the forces in the x direction. We have 240 minus 1.75 times 240 plus bx. And bx, just by definition, has to be 0.75 divided by, 0.75 divided by 1.75 times 240 newtons. Because if I solve this, I'm going to get 240 to the other side. And basically, I'm going to factor out the 240. So if I get those, let's see. Oh, yeah. I did this wrong. So we have, this is the positive. This is the positive x direction. So we have 240 minus, cx, which we just solved for, minus bx. So sorry about that. So yes, if I get bx to the other side, I can just change the equal sign. And then if I factor out this 240, I'm going to have 1 minus 1 divided by 1.75, which is the same thing as 1.75 divided by 1.75. That's what 1 is, minus 1 divided by 1.75. And I have 1.75 minus 1, that's 0.75. So I get 0.75 divided by 1.75 times this 240 newtons. So sweet. So this is my CX and BX. So let's just at least get these as a halfway decimal. Times 240. So CX is 137.14, and then we'll just do 2. With dot 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 means I didn't round. I just kind of gave up. That's how many digits I wanted to say. So 0.75 divided by 1.75 times 240. So this is going to be 102.857. All right, sweet. And so now the conclusion of this is that this is the pulling force. I mean, when I pull for 240, like this joint has to withstand that load of 137. And like if it is in equilibrium, if it's not moving, it's in equilibrium. Like I'm going to see 137 newtons there and 102 newtons there. What this problem says is at that load, if I, that's the load, if I just apply just a tiny bit more, both of those joints are going to break free. That means that the frictional component here, the force of friction, so let's say the force of friction at C, which is mu C times the normal component, which is Cy, we're saying that frictional component, so the frictional component at C equals the load at C. The load at C. So frictional component at C equals Cx. So cool. So right here we have Cx is equal to mu C times Cy. And then you can see that if we solve for the coefficient of static friction at C, we're going to have Cx divided by Cy. And if we do the same thing at B, we're going to have the coefficient of static friction at B is Bx divided by By. So we know what Bx is. We know what, so here's Bx and Cx. We got those two. Here's By. And then Cy we solve for somewhere. Did we not solve for Cy? I'm sure we did. Oh, maybe we didn't solve for it yet. Oh no, we solved for it on a different card. So hell yeah. So Cy is equal to 997.2 newtons. Alright, so we already solved for Cy. And now we're just good to go. So we have our two equations for the coefficient of static friction in relation to Bx and By and Cx and Cy. Alright, so let's do it. So coefficient of static friction at B is going to be 102.857 newtons divided by By, which is 981 newtons. Coefficient of static friction at C is going to be Cx, which is 137.142 newtons divided by Cy, which is 997.2 newtons. Alright, and in the longer video, like it's hella long, but we do go over like the why of what's going on, which is pretty sweet. Alright, so let's do this. So we have that 102. We're going to divide it by 981. And we're going to get a coefficient of 104.8. This one, we're going to get 137.1 divided by 997.2, and we're going to get 0.1375. And hell yeah, so this was the answers that were kind of given. No rhyme or reason for the significant digits. I think they were just thrown on the board. But hell yeah, this one and then this one rounds to 0.114 just to show you that, yep, so we did it. And I just wanted to do this fast as because I'm just doing this for a student. And then we do the longer video tomorrow. It's got to be more than 3 hours. It's crazy. But we just do what we do. And so I'm going to post this, so thanks for joining me. And hell yeah.